Okay, so picking up with where derivatives don't exist. One more time. Derivatives don't exist at discontinuities, corner points or cusps, vertical tangents. So shown below is the graph of y equal f of x. Where does f prime of x not exist? Where does f prime equal 0 and why? So let's go with the f prime does not exist first. Okay. F prime does not exist at. And I'll just work my way left to right. And the first place I get to, and this is the one students have a tendency to miss, is right there. Right there I have a vertical tangent, so it does not exist at x equal -5, and the reason is vertical tangent. That's what we mean by y. What's going on? Working my way left to right, the next place would be at that discontinuity, which looks like x equal -2. It's a discontinuity. Then we have x equals 0. Again, we have a discontinuity. Then I've got a corner point, which looks like at x equal 2. And then the last place will be where this asymptote is, and that's x equals 6, a discontinuity. And as we've said before, when we're looking at graphs, graphs are always ballpark. So if you said instead of 6, well, 6 is pretty clear. If you said the one that was x equal 2, you said x equal 3, I'm not going to ding you for that. So that's where the derivatives don't exist. Now the other part, f prime equals 0. Now, this isn't a great graph. I got lazy. This is supposed to be a very smooth transition right here. Not supposed to have a little bobble there. It's supposed to come down and look like the bottom of a parabola. So it's supposed to be a smoother transition. Maybe if I kind of color it in a little bit. I don't know if that helped or not. I don't know. It's supposed to be a smooth transition. And so right here, right there, we have a horizontal tangent. And we already talked about what horizontal tangents meant. Horizontal tangents, or how we found them, was set the derivative equal to 0 and solve. Horizontal tangent is telling you the derivative is 0. The derivative being 0 is telling you horizontal tangent. It goes both ways. Horizontal tangent, derivative 0, horizontal tangent. So f prime of x equals 0 at x equal 10 because we have a horizontal tangent. And there's that problem. Okay, next problem. Shown below is the graph of y equal f of x, which is made up of line segments. Okay, so we have f prime of x, or the graph of y equals f of x, which is made up of line segments. 1. Where does f of x fail to be differentiable, and why? And so that pretty much is what we just did. Now, we aren't going to worry about endpoints. Depending on how technical we want it to be, we can talk about left differentiability, right differentiability at the endpoints. I'm not going to go there. Just really concentrate on the things we already talked about, which is corner points, corner points, cusps, vertical tangents, discontinuity. And so the first one will be x equals 0. We have a corner point. Then x equal 3, corner point. And lastly, x equals 6, discontinuity. So, not differentiable at those guys, and we don't have a vertical tangent on this one. Corner points, cusps, discontinuities, vertical tangents. This one had corner points and a discontinuity. So that's where I'm not differentiable. Now the second question, where does f of x fail to be continuous and why? Well, it fails to be continuous at x equals 6, and I'm not going to be too picky on the y. We've got a jump discontinuity, but the actual y, if you think back to when we learned about continuity, it had those 3 steps, and it would be this, that the limit as x approaches 6 of f of x does not exist. Remember continuity 1, f of, in this case 6, f of 6 has to exist. 2, the limit as x goes to 6 of f of x exists. And here, left and right sides aren't matching up, so since my left and right sides are not matching up, I'm not going to have a limit. Now the point here is when I ask these 2 questions, invariably about a quarter of the class gives me the same answer for both of these. That they think differentiability and continuity are the same, and that is just not the case at all. Continuity, or where something is discontinuous, is just looking for gaps, breaks, and holes. Continuity doesn't care about corner points, it doesn't care about cusps, it doesn't care about vertical tangents. Continuity is just gaps, breaks, or holes. Being able to draw the picture without lifting your pencil, pen, or crayon. So here, the only discontinuity is there. Discontinuities are just gaps, breaks, and holes. It's differentiability that has so much more. Differentiability is the vertical tangents, is the corner points and cusps, and the discontinuities. Differentiability is bigger than continuity. So these are not the same, and that really is the point of these 2 things. And we have it down here. Note we see from the previous example it's possibly continuous at a point, but not differentiable. That we're continuous at 0 and 3. You know, we don't see 0 and 3 down here, so we're continuous at 0 and 3, but we didn't have a derivative. Not having a derivative is bigger, so to speak. In fact, a function that is differentiable everywhere is also continuous everywhere. But a curve that is continuous everywhere need not be differentiable everywhere. Because a continuous curve can have vertical tangents. A continuous curve can have corner points and cusps. If a curve has a corner point or cusp, it may be continuous, but it won't be differentiable at that corner point or cusp. Okay, got the same graph going on here. Shown below is the graph of y equals f of x, which is made up of line segments. Draw a graph of y prime of x, or draw a graph of y equal f prime of x. So clearly we aren't going to be able to use any sort of formulas and plug this into our calculator. We're going to have to use something else. I've got a graph. The primary graphical interpretation of the derivative is slopes. So we're going to work with slopes. And so I'm going to number this as section 1, section 2, section 3, section 4. Section 1, the slope. Just using the old-fashioned formula for slope, y2 minus y1 over x2 minus x1 is going to give me 5 minus 1 over 0 minus negative 4, and what that's going to be 1. And so what this tells me is, so from x equal negative 4 to x equals 0, f prime of x equals 1. That on that first section, the slope is 1, and so that's telling me that when I draw the derivative from x equals negative 4 to x equals 0, the slope, the derivative is going to be 1. Section 2, just using those 2 points there, what we've got 2 minus 5 over 3 minus 0, and what that's going to be negative 1. And so from x equals 0 to x equals 3, f prime of x equals negative 1. Section 3, you could do the same thing, find the slope, but it's horizontal. So m equals 0. So from x equals 3 to x equals 6, f prime is 0. And the same thing on this one, section 4. It's horizontal. So m equals 0. So from x equals 6 to x equals 10, f prime of x equals 0. So I've just started out. We can't see the picture anymore, but you should have these notes in front of you. What we did was we just looked at each section. Now, it was possible to do this because these were line segments and we could easily calculate the slopes. But what the slopes told us in each case is what the derivative had to be. We'll in this lecture or in this video here, and then we'll draw the graph on the next one.